I made a mistake, so I want to correct that right now. And this was, do you guys remember the one where it was 38% by mass hydrochloric acid? Yeah. It should be in your notes. You might want to find it because you want to fix this.
Oh, here we go.
Do you guys find that? Or know where to find it? We calculated the molarity first, and that part's fine. It's the molality calculation that I want to fix for you.
Oh, okay.
What I did with you guys that was wrong is I just took the density and I figured out the mass of the solution in kilograms, but it's mass of the solvent in molality. So I forget what the number was, but what was that number? Yeah, it was like 84 grams, right? Something like that.
0.08413.
Yeah. Well, if this is 38% by mass hydrochloric acid, that means it's 62% by mass water. Does that make sense? Which means that in 100 grams, there are 62 grams of water. Which is not 0.084, it's 0.062. Does that make sense to you guys?
Yep.
And this is the number that goes in the denominator here. Do you have the number, the moles of hydrochloric acid is 1.04 something, I think, right?
422.
0.04?
22.
22? So it's actually the whole point of molality is it's kilograms of solvent in the denominator, not kilograms of solution or anything like that. So it's solvent, not solution, which is the mistake that I made. But I fixed it now, hopefully. What got me thinking about this was Travis asked, because we got the same number for molarity and molality, and it's usually not. I thought it was just a coincidence, but it's wrong. Remember, the symbol for molality is a little m. And so this is quite different. We got, I think, 12.39 molar for the molarity. This is 16.81 molal, at least in hydrochloric acid. That fixes that. You also saw the demonstration of the different electrolytes, the light bulb. And one of the points of that was to illustrate the difference between a strong electrolyte and a weak electrolyte. For instance, the acetic acid, the one that barely glowed orange, I had to turn off the lights for you to see that. Everything there was 0.1 molar pretty much, right? 0.1 molar sodium chloride, 0.1 molar acetic acid, 0.1 molar of ammonium hydroxide. The 0.1 molar sodium chloride glowed brightly, 0.1 molar acetic acid did not glow brightly. And so what we concluded from that was that the 0.1 molar acetic acid must not be all dissociated. And I told you that, in fact, only about 1 out of 10,000 molecules of acetic acid at any given time are dissociated. That's what it means to be a weak electrolyte. A strong electrolyte pretty much completely dissociates into its component ions when it's in water. Sodium chloride, at least at that concentration, pretty much all of the sodium ions and all the chloride ions are dissociated from each other in the manner that I illustrated with the water molecules. Remember that illustration? So they're all pulled apart, so they all can carry a current from one of those wires to the other. We also have, so those are strong electrolytes, weak electrolytes. We also have non-electrolytes. These are things that don't dissociate into ions at all, and so don't carry a current. An example would be sucrose, sugar. You can dissolve sugar in water, right? And you guys probably all do it. But it doesn't carry a current. And that's because when sucrose dissolves into water, it stays as a complete molecule. There are no ions formed. What happens is pretty much the same process that I illustrated with the sodium chloride on the board. How the water molecules pull one away from the rest of the solid. Do you remember that picture? The difference is that it's not pulling, the water molecules are not pulling an ion away, but they're pulling an entire molecule away from the other molecules. And so the molecule stays intact, it's just dissociated from the rest of the molecules. Does that kind of make sense to you guys? No, maybe, maybe not. Let's see. That represents molecule sugar. I don't want to take the time to draw out the atomic entire structure. It's a molecule sugar. And there's a bunch of those, just like there are sodium and chloride ions in sodium chloride. They're all stuck together. What holds them together, for the most part, are the interactions between OH groups. They're called hydroxyl groups, oxygen with a hydrogen on it. It's a really polar part of the molecule. And those portions of this one sugar molecule interact with those portions of this sugar molecule and hold them together. There's a strong intermolecular attraction. That holds them together pretty well. When water comes along, it's going to have that same attraction for the hydroxyl groups, the OH, because water is basically one big hydroxyl group with an extra hydrogen, right? So it has this strong attraction. The oxygen is going to be attracted towards the hydrogen parts of the hydroxyl groups here. And the hydrogen to the oxygen part of the hydroxyl group. Make sense so far? So what happens is these attractions of the water molecules for these parts of the sugar molecule starts pulling it away from the rest of the solid, right? the crystalline sugar. And just like I showed you with the sodium ion, as this starts getting pulled away, more water molecules can now fit around it, and they start slipping in between and surrounding it, and eventually gets pulled pretty quickly, gets pulled entirely away from the rest of the sugar molecules. It's surrounded also with this sphere of solvation, sphere of hydration, the water molecules, this big group of water molecules, and now it's dissolved. But the point is, what's different here and with sodium chloride is this is not an ion. It does not have an electrical charge. So it can't carry a current between those two wires in that setup. So it won't conduct electricity. It's what we call a non-electrolyte. Does that make sense? Maybe? No? Yeah. I'm going to assume that it does. So there's a list on page 400 that is basically a guideline to tell if something is a strong electrolyte or not. Should you memorize it or know it, put it on your card, what have you.
What page was it?
Sorry, page 400.
400.
For instance, the first rule tells you that it gives you that, and that's probably the most useful rule. It tells you that hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid are all strong acids, which means strong electrolytes. And it also tells you that if it's an acid and it's not in that list, then it's not a strong electrolyte.
Sure.
This is a list of the acids that are strong acids, which means that they're strong electrolytes, which means that in solution, they essentially completely dissociate into the hydrogen ions and the polyatomic ion or the anion. Like hydrochloric acid will, in solution, completely dissociates into hydrogen ion and chloride ion. Nitric acid into hydrogen ion and nitrate ion, and so on. If it's an acid, but it's not in that list, then it's a weak electrolyte, which means a weak acid, which means it's like acetic acid that I was showing you guys last Wednesday. Most of the molecules are going to be not dissociated, a few will be dissociated. That means if you have the same concentration of a strong acid, say 0.1 molar, of a strong acid and a weak acid, two different solutions, there are going to be more hydrogen ions in the strong acid solution than there are going to be in the weak acid solution. Because all of the strong acid molecules will have dissociated to form hydrogen ions, but the weak acid molecules won't have. The rest of the rules here, definitely know them, but you can more or less predict them based on the solubility rules that we already learned, that you're putting on your card for the test, right? If something is soluble, then it's going to be more or less going to be a strong electrolyte. I'm not sure. Do you guys remember that they listed some things that were partially soluble? And those listed solubility rules? Now we know what that means. Those are weak electrolytes. The rest of this chapter I can talk about by working, I think, just a few examples with you, and that'll illustrate the points in this chapter. It'll also, at least a couple of them, will help you with some homework problems that you're going to run across, because they're going to be similar. But the basic idea in this whole chapter is, well, solubility, electrolytes, and using molarity as a way of telling you how many moles of something you have. For instance, you know the limiting reactant problems that we've done, percent yield and so on, theoretical yield. If it's to find the limiting reactant, what I told you is find the moles of each reactant and divide by their coefficient. You guys remember that? Well, up to this point, we've been mostly giving you the amounts of the reactants in terms of grams, right? Now that we are more comfortable with molarity, it's another way of giving you the moles of the reactants is to tell you the volume and the molarity. Moles per liter times liters is moles, right? So that's all that's really different here. I'm going to work out a titration problem with you. You've done this in lab last week, but I want to make sure, because it's a really important kind of calculation for 101. You really have to be able to do titration calculations. As you already know from lab, in a titration, you typically, most typical titrations involve a solution where you know the concentration of one but not the other. And you perform a measured reaction where you reach the end point. You guys remember what the end point is from the lab? Yeah, it's when you've added just enough moles of one reactant to use up the second reactant. So in the lab that you guys did last week, the first part with the KHP and the sodium hydroxide, you guys remember that one? Remember that? What you did was you measured out the mass of some KHP, and using the molar mass, you were able to figure out how many moles you had, right? You put the water in, you put the phenolphthalein, the indicator in, it was clear. Then you put the sodium hydroxide that you had made up in the burette, and you added it until one drop made it turn pink, right? That was the end point. The reason it turned pink is because you had added just enough moles of sodium hydroxide to use up all the KHP. And then there was a little bit excess, which made it basic, which made it turn pink. So that end point was when you had added just how many moles of sodium hydroxide you needed to react with the KHP. You might see it called the equivalence point too. And just as in the lab, the reason that the end point is important is because if you know how many moles of the second reactant were in the solution, then because you've reached the end point, just reached the end point, not overshot it, right? Then you know how many moles of the first reactant you've added. And what you guys did in lab last week is you used a burette to measure how many milliliters of that sodium hydroxide solution you added to reach the end point. That means you knew the volume that you added. You know the moles, you know the volume, That gives you the molarity. That's the concentration. So let me work out an example. So what do you guys think? How are we going to approach this? What's the first thing that we're going to need?
Milliliters to liters.
That's
Oh.
certainly something we're going to want to do. That's kind of a detail now that we're going to do in the middle there, but kind of a bigger picture. What do we need to know first before we can do any of that stuff?
How many grams of sulfuric acid react with sodium hydroxide?
How many grams?
Or-
21 grams?
How many milliliters?
Milliliters?
We just need to find the balance equation.
There, yeah, balance equation, that's what I wanted. That's what I want. And the reason, why do we need a balanced equation? The ratio, the mole-to-mole ratio, good, right? So, what's the formula for sulfuric acid?
H2SO4.
2SO4. Sodium hydroxide, you guys, sure. What are the products?
H2O.
Yep. What else?
That is sodium sulfate.
Sulfate. That, right? Need 2 there to balance that, I think 2 here. All right, so now we know the mole-to-mole ratio, right? The picture now, the picture of what's going on. I think the titration is good to have the picture. You have your sulfuric acid solution down here in the beaker, 25.00 milliliters. You probably measured it out with a volumetric pipette or a pipette or something. Sodium hydroxide's up here. You have your indicator in here. You know, do the titration. 1 drop makes it turn pink. The amount of sodium hydroxide, the final burette reading minus the initial burette reading was, what, 29.12 milliliters. So we know the volume and molarity of sodium hydroxide it took to reach the endpoint. That's volume and molarity is just another way of saying moles, right? So we know moles of sodium hydroxide. Because we have a balanced equation, we have a mole-to-mole ratio, we can calculate how many moles of sulfuric acid there were here. We know the volume because we measured it out. The moles over the liters gives us the molarity. That's all there is to it, right? Let's do it. If it's okay with you, I'm just going to move the decimal 3 places to the left to change the milliliters to liters. You guys comfortable with that?
Yeah.
All right, so now we know how many moles of sodium hydroxide, right, liters of solution cancels. From the mole-to-mole ratio, we can get moles of sulfuric acid. Last step, take the moles, divide by the liters, right? It was 25 milliliters, so that's 0.02500 liters. And so the concentration of sulfuric acid was 2.81 molar in that battery acid. I believe you have some homework problems to ask you to do essentially the same thing that you did with experiment 22B last week. That's the one where you had the solid acid and you figured out the molecular mass or molecular weight of that acid. You guys remember that calculation? Make sure, when you get there, if you're not sure how to do it, look back in your notebook. That's how you find it. So that's that one. This next problem. This is one I really want to show you because a lot of people get hung up when they see this. I believe there's a homework problem similar to this. so do you guys understand the picture of the setup? You understand what this is describing? You have a sample. It's a mixture. It's a white salt, right? It looks pretty much like table salt. It's going to be sodium, but it's a mixture of potassium iodide and sodium bromide. What you do is you take that, and it weighs 0.5199 grams. Take that, put it into the beaker, and add enough water to dissolve it all. So it's all dissolved, right? And when you dissolve it, because both potassium iodide and sodium bromide are soluble, what you have are the ions floating around. Take that beaker with the ions floating in it, and you titrate it with a solution of silver nitrate. And the concentration of silver nitrate in there is 0.062199 molar. Okay, so silver nitrate is soluble, which means it's basically a solution of silver ions and nitrate ions. As you add that solution, what happens is silver ion, if it bumps into an iodide ion, it's going to precipitate out, it's going to form a solid because silver iodide is insoluble. The same thing with bromide. Silver bromide is also insoluble. So as you add this silver nitrate, you start getting this solid form. Right? Some of it's silver iodide, some of it's silver bromide. And you keep doing that until you've reached the end point. In other words, you've added just enough silver to precipitate out all of the bromide and the iodide, but no more. And that amount that it takes is 62.10 milliliters. Okay, so far? So what we know is how many moles of silver we added. Now, this sounds like it's jumping, but what we ultimately want to find is what the mass percent of potassium iodide and sodium bromide was in the original sample, that 0.5199 grams, right? So, how would you start thinking about this? What's the first thing you'd want to think about to try to find a way to solve this? Yeah, okay. Before I start just kind of like randomly calculating stuff, I'd like to know where I'm going, right? That's usually what I start with. And so what do I want to find? The mass percent, which means, I think that said that I need the mass of the potassium iodide, and I need the mass of the sodium bromide, right? Because the mass percent is just the mass of the component divided by the mass of the whole times 100. We know how much the whole weighs, the 0.5199 grams. All we have to do is find out how much of that's potassium iodide and how much of it's sodium bromide, right? So really, our goal is to find out how much, say, potassium iodide there is. If we know that, then we can get the other if we need it, because it's just 0.5199 minus that. Does that make sense? So really, we've set our goal, right? We've figured out our goal, and we've made it, just one thing. Mass of, pick one. Let's pick potassium iodide. So that's what we have to find. So that's where we want to get to. What do we know? Right? Can we easily calculate it? What am I basically telling you here?
Moles of
silver, right?
Yeah.
And I'm saying silver because it's the silver that's reacting, and this whole thing's a 1-to-1 mole ratio, right? Let's just do that right now, get it out of the way. Put it in my memory and come back to it. All right, so now, we know how many moles of silver. We need mass of potassium iodide. Well, we can always get the mass if we know the moles, right? So maybe all we really need is moles of potassium iodide. But because in potassium iodide, there's 1 mole of potassium iodide for every 1 mole of iodide, right? Really, if we have moles of iodide, then we can get that. So now we've refined what we need. We need to figure out how many moles of iodide we have in there. Well, what do we know? We do know that how many moles of silver we added. But the problem is that it's reacting not with iodide, but also with bromide. So we need some sort of way to get past that. Let me show you how I approached it. I set up an algebraic equation or two. Okay. Does that make sense what I'm saying there with that equation? Moles of silver that we added at the end point, which is where we're at, is equal to the moles of iodide plus bromide. Right? No, let me not do this. Let me follow it this way. We also know that the total mass equals okay. Does that make sense? If there's two things in there, they have to add up to be the total mass. Right? Let's call the mass of potassium iodide. That's what we want, right? Let's call it X, right? It's just going to be the moles of potassium iodide, which is equal to the moles of iodide. Is just equal to the mass of potassium iodide divided by its molar mass. Grams over grams per mole is moles. You guys buy that part? Let's see. 166.00277. Does this make sense to you guys? The moles of potassium iodide is equal to the moles of iodide. The moles of potassium iodide is the mass divided by the molar mass. Right? Let me rearrange this. So I'm taking this equation up here, and I'm just rearranging it so that I get the mass of sodium bromide in terms of X. You guys see what I did there? The reason I want to do that is because I want to come down here, get moles of bromide, same as moles of sodium bromide. This is the moles of sodium bromide is going to be the grams of sodium bromide divided by the molar mass of sodium bromide. Okay? Yeah, right? Is that okay? Grams over grams per mole. This is the mass of sodium bromide is just this. It has X in it, right? Mass of sodium bromide. You guys follow that so far? What's nice about this is now I can come back up here. We already know this number. We figured it out over there, right? Now we have both of these terms in terms of just one variable, x. So now it's just a simple matter of plugging these terms in up here, plugging this number in, solving for x. What's x again? Mass of potassium iodide, which I erased it, but that's our goal, right? We can get that, we can get the mass percent easy. You see how that works? You have a homework problem, at least one homework problem, that where you're going to have to do this. It's a mixture of salts and same things happening. So let's finish it out. Now it's algebra. Is that okay? After some algebra, I'm going to let you guys do that. If you get stuck, I'll show it to you. I don't want to take class time just doing algebra. Solid, I believe this is what you get. That means that the mass percent the mass of potassium iodide is the mass of potassium iodide, the total mass. So I get 61.97% potassium iodide, which means it's going to be 38.03 mass percent sodium bromide. So at least get that in your notes so when you run into that homework problem, you can look back and you can figure out what to do. that's chapter 12. So we have time, about a half hour or so, and I'd like to use this to answer any questions or go over anything you need to go over for the exam. So get ready for Wednesday. Remember Wednesday, get here a little bit early. Bring your Scantron 882, your card if you want it, 3-inch. Remember, it has to be 3-inch by 5-inch actual index card. It can't be a piece of paper or anything like that. Both sides, pencils, calculator.
We're gonna have one that's exactly like that. A problem.
This is chapter 12. We won't go through
Oh,
chapter
it's
11
not.
on the exam.
Okay, yes.
The exam's chapters 8, 9, 10, and 11. Jessica.
Do you guys have the activity series?
I'll give you the activity series.
And then what about the molecular orbital?
I know we do.
Yes, you should have the, or no, the 2 molecular orbital energy level diagrams for the first and second row diatomics. Remember those? There's 2 different ones, one for up through nitrogen, the other for oxygen, fluorine, and neon. And remember, the way that I ask you to do it, the way that I'm going to ask you to do it on the exam, is if you have a heteronuclear diatomic, where one of the elements is, for, nitrogen or before, and the other one is oxygen or after, use the molecular orbital energy level diagram for oxygen, fluorine, and neon. Okay? If one of the elements is oxygen, fluorine, and neon, use that diagram.
So are you giving those to us, or do you have?
No, you should know that or have it on your card or something. So I'm not going to give you the molecular orbital energy level diagrams.
Can you
What else
give
do you have?
an example of a chiral? I forgot what it's called exactly. Chirality?
Chirality.
Oh, chiral.
Chirality.
Sorry.
Yeah, that's okay.
Anyway, that. An example
Yeah,
of
you
one
want
else.
to see an example?
Yeah.
The one that's after you.
What happened?
I don't know.
It was like really simple.
No,
I got
no,
it wrong.
it's not.
I had to get up on that.
The sucralose one, the sugar one, where you have to do the 3D models.
Yeah,
Yeah,
I
that
think
one.
that was
That's
pretty
weird.
difficult.
That one's pretty hard.
That was only one of them too, right?
Yeah.
Okay, cloud. I don't have to know how to process.
Nah.
Are you comfortable with the line drawings?
Yeah.
Yeah.
Yeah, like as a double bond or like what do you mean?
Like this.
Carbons.
Yeah, I get those.
Okay. Cool.
So that's C5. Yeah. Yeah.
So the question might be, which, if any, of these are chiral carbons, chirality centers?
Yeah.
And remember the rule that I gave you that'll work for you in here is if you have a carbon that has 4 different groups on it, no matter how different, just a little difference, okay, then that carbon is a chiral carbon, it's the chirality center. And remember, for just in case you don't remember, for these line drawings, the carbons are the ends or the angles, and we always assume that every carbon has 4 bonds to it. So any bonds that you don't see, you have to assume that they're hydrogens. They are in these drawings. Like this carbon here has only 1 bond, so there's 3 hydrogens on it. Okay? So which, if any, of these carbons has 4 different groups and thus is a chiral center?
Are they each unique? The one with BR is the chirality center, right?
This I agree. This would be a chirality center because this carbon right here has a bromine, has a CH2CH3, has a hydrogen, right? And it has this other group here, which is different than the CH2CH3. Is that
The hydrogen's behind that corner. You can't see it, right?
if you want?
Yeah.
If you wish.
Works for me.
Yeah, that's right. That's
Yeah.
right. Yeah. I don't care what you want.
Oh wow.
Yes, do you guys, so
Yeah, it's pretty simple.
are there any others, or is that it? Just which one here?
Where you were,
Here,
up to the
up to the right.
right?
That one, yeah,
Yep.
I agree. Because this carbon right here has a CH3, it has a CH2CH3, and it has a C with a bromine and other stuff on it, right? Plus, it has a hydrogen. There are 4 different groups, so that also is a chirality center. 2. question could be on the multiple choice test. How many chirality centers does the following molecule have? 0, 1, 2, 3, 4. None of the above.
Test is going to be the line drawing. Could it be?
If I draw anything, it will be probably line drawings because it's easier for me to draw.
Do we have to memorize the solubility rules?
Yes, the solubility rules should either be on your card or memorized, definitely. I think Adam was telling me that he took the solubility rules from Sapling and condensed them down and put them on your card. That works. What else do you guys want to know?
If you get your card,
Examples, any Sapling stuff that you're working
I
on?
have all this stuff online. I've been on the computer.
Calculate
I might actually do that. That's a good idea. Because I thought it's some practical, but it's doable. That's awesome.
One of the elements molecular
You just
formula.
screen and trick it. Yeah, that would be a good idea. It took me like half hour.
Calculate based on those two numbers.
What'd you do?
To use the
I just
factor.
clicked on the solubility rules. I basically just copied it on my index card. It
Like,
took
are you talking about when you have to multiply?
So
Yeah,
if you're willing
it's a
to
number of
like
Excel.
sacrifice that, but
Like say
there's not
like
really
two
much
or three.
information in this chapter.
Yeah.
Yeah,
And then
it was too vague.
molecular formula for condensing.
Right.
Willing
So
to
you multiply
deploy
by
it
two
on
or three or
Sapling,
something,
in my
right?
opinion. Like it's just a
It's
grid.
okay to multiply.
Oh yeah,
Well,
you just have to match it up,
Yes.
and that's it. I might just do a roll because I
What
did
else?
that last semester.
Do
Yeah,
eight.
I fucked up. Like I tried to do that, and I got
8
on
and
the
68
test,
in chapter
and
8.
It didn't help me. The grid. Yeah, it didn't really. It had stuff missing, so that was my own fault. But Sapling probably is a good one. I took the one from the book. Yeah. I guess just do it at your own risk. Yeah. Yeah. I don't trust it, you know. Yeah. See, I didn't trust the solubility rules in this book. I was like, I don't know, because on the homework, I'm like, that doesn't make sense. Like, that should be
Well,
aqueous.
whatever one you pick, you're going to have to draw the Lewis structure.
Maybe I should do them. I don't know. I'll figure it out tonight.
This is selenium hexafluoride. Selenium has 6 valence electrons, each fluorine has 7. That's 48 total. Minus 2, 4, 6, 8, 10, 12. Each fluorine needs 6 more.
This is
6, 12, 18, 24, 30, 36. That's
Two
what we
is
have.
the bonding groups right there, and the lone pairs with the angles and everything. Wow. Yeah, that's awesome. Yeah, this one helped too. Did you use that picture? Just yeah. Yeah, it's a good idea. Or copy that at least, but the same deal. Yeah.
The octet rule is satisfied for everything. Calculating formal charges. Each fluorine has 7 valence electrons, minus 6 dots, and 1 line is 0. So every fluorine has a 0 formal charge. Selenium has 6 valence electrons, minus 6 lines is also 0. It's the best you're going to do. Okay, so this is a good Lewis structure. So now we know that the Lewis structure has selenium in the center, has 6 bonds to it, no lone pairs. So in terms of geometry, it's going to be, what's the molecular geometry going to be?
Octahedral.
Octahedral, right? And that means that the bond angles in octahedral, that there's going to be 90-degree bond angles, and, well, 90 degree all the way around, really. The 180 from the two here. So the answer to that would be it has 90-degree, number 1, and exactly 180, number 8. You wanted something that was less.
No, I think the answer in the back, it said 1 and 2.
No, not for, can't be for selenium hexafluoride.
So it says 6, 8, and part A says 1 and 2. Exactly 9.
Okay, I believe you. I'm gonna look at it.
The book's wrong?
Oh, see, that's why it's confusing.
What's wrong with it?
68A should be 1 and 8, not 1 and 2. Everything's symmetrical. There's nothing to distort it from the ideal shape.
Do we need to know the molecular orbital theory
2 minus 0 equals 3. Is
equation?
that what you're trying to say?
The bond order.
It's psi squared.
Say it again.
Like, what's the
Oh, Schrödinger's equation?
yeah, sure.
No.
Oh, we don't need.
Not sure. H psi equals E psi, that thing?
Yeah.
Isn't that what we're trying to figure out?
What else? Just
What's the difference between a redox and a single reaction?
oh, redox and a sin.
Isn't there a single alcohol by itself?
Say that again?
Isn't there, in both reactions, aren't there a single alcohol by itself?
Actually, okay, sometimes. Single displacement or single replacement reaction is a specific example of a redox reaction. Some redox reactions are different. For instance, combustion. Well, that's a single element too, but they're not always a single element. There are redox reactions where it's two compounds reacting. So that's a bigger class than single displacement. For us, okay. When you get to 102, you'll learn to calculate something called oxidation numbers. But for this test, for this class, the way that you can tell if it's a redox reaction is, well, if the number of electrons is changing, and you're going to know that if it's ionic compounds and the charge is changing on the ions, like iron 2 going to iron 3 or something like that. Anything reacting with just oxygen, like a combustion reaction, that's a redox reaction. And then the single replacement reactions. That's how you know for now. We'll do better for you in Chem 102, but for this one, that's how you do.
The activity series for halogens, it's more reactive and more down.
No, the highest, it's just like the activity series in your book for the metals. The fluorine's more active than chlorine, which is more active than bromine, which is more active than iodine. What else?
For precipitation reactions, it has to be two aqueous solutions to form that solid.
That's what precipitation reaction.
Okay, all right.
Can you do an empirical formula one?
Those I can't make up out of my head. If you have one,
I can show you.
Yeah.
Do you want to see it or?
Yes, please. Or you can get it.
Tomorrow? Yeah, probably next week.
Not 54.5%.
Did you guys want to do one today? Oh, okay, yeah, me too.
Yeah.
Tomorrow?
9.15%.
Can we have a math exam? Yeah, we do.
36.32.
That's what I'm studying for tonight. But yeah, tomorrow, definitely.
So the question is, what's the empirical formula to give this mass percent
Another one?
composition?
There's no other day
So
left.
percent
Yeah,
grams times the moles divided by the smalls. That's the procedure.
Yeah, I'll post some details tonight on the Facebook group.
Oh, sure.
Yeah, sure.
Oh, okay, so this is.
What happened? I kept those notes. They were getting so
That's not far. Don't worry about that.
Also, like, I kept them in the back seat of my car. It's like I never actually, like, I try to study them, but I never actually ever
Do
copied
you want to
them.
look at them?
Yeah, I was just gonna take a picture of them.
You can
That's
just
okay.
borrow them out.
I'm sure
I
you're
have
gonna.
everything I need for the test.
Are you sure?
Yeah. just to make sure. Yeah, I should be alright.
Okay, thank God. I charged him like a one piece.
It's no problem.
Yeah, I'm not gonna make it this time.
So that's,
It's true.
So now that we've calculated moles of each element, let's divide the smallest into the others. Smallest number of moles is oxygen, so we divide it into moles of carbon and moles of hydrogen.
by ground state.
It's reactant. What is it called?
Limiting reactant?
Limiting reactant,
Yeah.
right?
Yeah, just the small
Same
amount of
thing
moles.
as vanilla? Or is it different?
Similar concept.
It's even shorter than that, though, I think.
Oh, really?
Yeah, because you just find the smallest amount of moles.
Oh.
And then for the actual yield over the theoretical yield,
This is
and you remember that.
1.999.
Theoretical yield, it's the same thing as a limiting reactant. You just plug it into another formula.
Yeah, how does this distinguish between the
And then hydrogen.
Well, this is how you do theoretical yield, this one.
this one here?
It's the same idea, yeah. You're just, you're dividing by the smallest number of moles,
Yeah.
just so you can determine how many moles of each is in the empirical formula. Because once you
This is
determine how many moles of carbon,
3.998,
how
so
many
that's
moles of
4.
oxygen, how many moles of hydrogen, you know how many moles. I mean, you can write the empirical formula. You'll see when he finishes it.
And that gives us the empirical formula.
I need to copy this off.
Yeah, you probably should.
Okay, so you can just round whenever you don't have to be that
Well,
precise.
the rule is that when you do this division right here, if the decimal number you get is less than 0.1 from a whole number, closer than 0.1 to a whole number, then you can just round. If it's 0.1 or farther, then you have to multiply by some number. So, but here it was. What else?
Will it take long to review the vector theory?
Even the geometries? Well, I mean, in general, is that what you're talking about? Yeah. So Vesper theory, the geometries, you need a Lewis structure. So I'll give you the formula to draw the Lewis structure. Make sure you have the best one. Count the number of electron groups on the central atom. And remember, electron group is either a lone pair or a bond. It doesn't matter. A double bond just is one electron group. A triple bond is just one electron group, right? So count the electron groups, lone pairs and bonds. And then you either have to have memorized or have on your card that table. So you find the number of electron groups, gives you the electron group geometry. And then to get the shape, then you go back and see how many of those electron groups are lone pairs. And that gives you the molecular geometry. So it's all using that table right there. That's all you do. Lewis structure, count the electron groups, see how many are lone pairs, go into the table and find it. That makes sense? Do you guys remember that? So is that what you were asking for? You think so? Go to the table. I don't remember where that table is, but that's a real important table that I would definitely have on my card. Chapter 8.
Do you want to get it?
You guys know what table I'm talking about.
Yeah.
An example where
It's page 245.
finding the limiting reactant.
It's on 245. The table, yeah.
Page 245. Either that or
So because the previous one asks for,
246, same thing though. I think I put one on the board that was a little bit different, but they all work. So limiting reactant. So I could either ask you for the limiting reactant, or I could ask you for the theoretical yield, or I could ask you the percent yield. All of those would use as limiting reactants, no problem. But just limiting reactant? Yes.
So what you're gonna do?
Put the 2 parts, right?
Basically, you just take this. Say you have 100 grams of substance. So that would mean that if you have 54, what's that? 83? Yeah, no, that looks like 83. That would mean that you have 54.83 grams because it's 54.83%.
Oh yeah, that's it. I get that part.
Okay, so all you're doing is just assuming that you have 100 grams. Divide by the molar mass to give you the moles.
Yeah. So these are all
This is all
equations for
mole.
moles too.
Yeah, easy.
Yeah.
9.15 grams of hydrogen over. Yeah. Or you know, take some this way. And then you're going to divide by this smallest number.
And this is going to say a zero because they're asked then like 2
I mean, this is, so an limiting reactant problem like this, it probably won't give you the balanced equation. You're going to have to come up with it yourself. So what are the reactants here? Zinc
What is this?
and
Which is
salt,
what
right? And hydrochloric acid.
You're just
What kind of reaction is this?
So this is very formula.
Single replacement reaction. So that means that the zinc, which element is it going to displace? Hydrogen, right? And that gives us zinc chloride. And what's the other product? Hydrogen gas. Balancing it. That does it, right? So you need a balanced equation always for limiting reactant type problems. Remember, the procedure is, once you have a balanced equation, find the moles of each reactant, then divide by their coefficients in the balanced equation. Whichever gives you the smallest number, that's the limiting reactant. So, zinc. I gave you a mass, so to get the moles, you just take the mass divided by the molar mass. .38 is what this is.
Yeah.
The coefficient for zinc is 1, so it's just the same number. Hydrochloric acid, I gave you a volume and a molarity, so the moles is just going to be the liters times the moles per liter. Change that to 48.1 and 0.5 molar. And the coefficient for hydrochloric acid is 2, so dividing this by 2. Which is some number smaller than this, and so we know the limiting reactant is hydrochloric acid.
Can you go one step further and just do a theoretical yield?
So if you ask for the theoretical yield, find the limiting reactant first, assuming you're given amounts of both reactants. And then use the moles, you always use the moles of your limiting reactant as your starting point. And so, now that we know that hydrochloric acid is the limiting reactant, we use that for the starting point. And so I'm going to take the moles of hydrochloric acid times the mole ratio to get moles of hydrogen, and then multiply it times the molar mass of hydrogen to get the theoretical yield. So, theoretically, yeah. If it was a percent yield, I would have to also give you the actual yield. Just take actual theoretical. What else? Make sure you finish the homework before 2:20 on Wednesday. That's the deadline. After that,